Okay. Okay, so let's start the second session of today's program. So we have two speakers as usual in this session. And the first speaker is Benjamin Doyon. And he's going to talk about correlation functions from hydrodynamics beyond the Boltzmann-Gibbs paradigm. So please start.
Yeah, thank you. So it's a pleasure to give a talk at this conference, very interesting conference. So what I'm going to talk about is actually something relatively simple. I won't go into a lot of technical details, but I want to extract the main ideas, some kind of slightly newer ideas about how to evaluate correlation functions in the large scale of space-time using hydrodynamics principle. Okay, there's something called the Boltzmann-Gibbs principle. Here I call it paradigm, which is the basic things that people can use in order to evaluate correlation functions. But I want to go beyond that and see how this works. Okay, so my basic setup is very simple. I'm thinking about some Hamiltonian system in one dimension. Of course, a lot of the things that I will say would apply as well in higher dimension, although perhaps not all, but I'm right now focusing on one-dimensional systems. The system may be integrable or not, although what I'm going to talk about more precisely would be an integrable model, but the general principles are valid beyond integrability. They are based on hydrodynamics only. Okay, so I have an infinite long system in one dimension. There's a certain number of conservation laws. So, energy, particle, momentum, and they can be higher conservation laws. Supposedly local conservation laws. So they satisfy some conservation equation, density and current. And I will be considering correlation functions in this system. In fact, 2-point correlation functions. Now, correlation functions, you need to specify the state. So I will be just thinking about thermal states. So it's relatively simple. Thermal state correlation functions in a many-body interacting systems. Now, the state may be a GGE as well, and all the principles I'm going to talk about are valid kind of more generally. Okay. Now, so to be more precise, so what I'm looking to study are 2-point correlation functions of local observables in space-time. So there's a lot of techniques in the context of integrability that have been developed to evaluate correlation functions, but a lot of these techniques are valid, first of all, at 0 temperature for a lot of these techniques, and for a lot of these techniques also valid at 0 time in pure space. Okay? So here I'm thinking about finite temperature or finite density and dynamical correlation functions. So these are connected correlation functions of, in principle, arbitrary observable. And I'm looking at a large space-time. So this is the region where you can expect things to simplify and some general principles to apply. So what is large space-time? Here I'll be looking at hyperbolic scaling where x integral to infinity with x over t fixed. So of course you would think there that something like Euler hydrodynamics, which is hyperbolic scaling, should give you some information about this correlation function. And indeed, that's somehow what I want to explain, how Euler hydrodynamics can give you information about such correlation functions. So the point is to try to find general principles that tell you what asymptotics of correlation functions are, and that are based on essentially on hydrodynamics, without having to do a priori microscopic calculation, difficult calculation using Bethe ansatz and using all that. Okay. And sometimes even these calculations are not even available. Okay, so this is so correlation functions in many-body quantum systems. Well, a lot of the principles I talk about actually are valid for classical or quantum, but I'm going to focus on quantum systems and their large-scale physics. Now, I want to introduce some new principles, and in order to do that, it's actually pretty useful to have an explicit model. So somehow that is something that is very explicit, where explicit formulas can be obtained to check these principles. And there is a model that is relatively simple, which is the one that I'll concentrate on. So this is the XX quantum chain. It is relatively simple because, well, first of all, it is integrable. In fact, more than that, it has an underlying free fermion structure. So because it is free fermion, essentially everything can be calculated. Okay, so you can calculate a lot of things and then try to see if you can, check the general hydrodynamic principles against these exact calculations. That's the idea, right? So it is kind of possible nowadays to do that because we know that even if a model is free fermion or integrable, there is a notion of hydrodynamics for that. It is generalized hydrodynamics. So you can have general principles of hydrodynamics and apply them to GHD, and then specialize to free fermion and see if this works. And that's what I'm going to do. So first of all, let me just tell you about correlation function in this model. So it turns out that some correlation functions in this model are rather easy to calculate, kind of elementary school, maybe not elementary school, but master level kind of calculation. For instance, this one, sigma 3, sigma 3. So let me kind of use my, this one, sigma 3, is relatively simple to evaluate. So these are the Pauli matrices. This is one-dimensional chain. There's a kind of some interaction, but because it can be fermionized, it simplifies a lot. And sigma 3, it turns out, is just a bilinear of fermions. So using Wick's theorem, you can calculate this correlation function exactly, and you can look at its large space-time hyperbolic scaling asymptotics. And this is a formula that you get. Okay, so there's nothing especially amazing about this formula. Just two things to notice. Well, a few things to notice. First of all, there's a 1/t. Okay, so this correlation function in the region of space-time, in the time-like region of space-time, so where time is greater than 4x. This is my psi is x over t, and it's between minus 4 and 4. Is greater than x over 4. Time is greater than x over 4. In that region, this correlation function decays like 1/t with some factor that depends on which ray you're looking at. So basically, I look at space-time, there's x and t, and I look at some point there on that ray. That's the ray psi, and how it decays when you're very far along this line. Now, so it decays like 1/t, so that suggests kind of earlier hydrodynamics type of scaling. Okay, but there are a few terms in this factor. Okay? There's a factor there's a term which is something that looks like some free energy or some hydrodynamic, some thermodynamic quantity, where you have a filling, which is just a thermal filling for this 2-point function, some particular type of filling. And this term it's nice and monotonic, but there's another term which is oscillating. So here there's some oscillation. So there are different type of terms which you can calculate, and these two type of terms. And then you can wonder, is it possible to get, instead of doing a Wick's theorem calculation, which is simple, can you interpret these terms in a general fashion using hydrodynamics? And therefore, then use these general principles in more complicated systems. Okay? So these are two terms that we get from this 2-point function. Now, there's another 2-point function that has been calculated and studied in the past, is the one involving sigma 1 and sigma 2 in this particular model. Now, as it turns out, this one is a bit more complicated, and maybe you cannot give that to a master student, but maybe it's a PhD student or PhD thesis or something like that. And this other correlation function is, you can write it in terms of sigma plus, sigma minus. Okay, sigma plus, sigma minus in space-time, x over t. And here, actually, you don't have to look just in the time-like regime to get 1/t decay. And by the way, if I come back here, if I look here in space-like regime for psi greater than 4, I would find an exponential decay, but I'm not going to discuss about that. Okay? So here you look in everywhere in space-time, and everywhere in space-time, what you find is always an exponential decay in this finite temperature state. Okay? So there's some complicated formula. Of course, you don't have to look at all the details of the formula. That is not important at all. But what is important is that this is an exponential decay. So you have exponential. There's in the time-like region where xi is more than 4, there's a t exponential decay in t times some prefactor. That depends on temperature. In space-like region, there's also exponential decay. There's an x there times some prefactor. And the prefactor depends here on the magnetic field. So the model has some magnetic field, this magnetic field there. Turns out that prefactor depends on the magnetic field. Now, these two formulas were obtained by analyzing asymptotics of Freedom determinant. So this correlation function, because of the free fermion structure, can be written as a Freedom determinant. And then you can use various aspects of the theory of Freedom determinants in order to evaluate the large spacetime asymptotics, and this was obtained. As it turns out, for some reason, in the regime in the space-like regime with magnetic field greater than 2, the asymptotic of Freedom determinant was never analyzed in the literature. So we have not found any asymptotic in the literature for this, although supposedly it is possible to do. But we have found a result, which is this one. And this result actually looks a bit different from these two results. There's an additional exponential, and presumably the asymptotic of Freedom determinant is a bit more complicated to analyze, and that's why it was not written. We have found that, however, is not a kind of a macroscopic calculation. This is from hydrodynamics. So this is the kind of hydrodynamics result, which I'm going to explain. Okay. So these are the results for this two-point function. They are very different, of course, as you can see from the other result for the sigma t, sigma 3. One is 1 over t. The other is exponential decay. Okay. But this can be evaluated in at least, well, in various ways using various techniques because this is free Fermion. Now the question is, can we interpret these results using hydrodynamics? Are there some general principles that allow us to understand these results? These general principles, then you can go beyond the XX model. Okay, but I'm going to just stay with the XX model. Okay. Are there any questions?
Trivial question.
Yeah.
So can you also reproduce the known results by this hydrodynamic arguments?
If we can, sorry, repeat.
Can you also reproduce the known results too?
Yes, yes, indeed. So what I want to say, so the goal of my talk, let's say, is to explain how we can reproduce, so from hydrodynamics, also this. Yes.
Yeah.
So
okay.
the full thing, essentially. Yeah. Mm-hmm. and also kind of, also all of this. For different hydrodynamic principle. Other questions?
So this is the
yeah.
Sorry. So is the magnetic field necessary to make it sort of non-trivial, or it's equally?
No. Actually, you can take zero magnetic field. It is still non-trivial. Actually, like this two-point function is still non-trivial. It's still kind of a non-trivial to calculate, and was for this h equals 0 is included in this in these two formula essentially, and this was considered then by its Scorpion. In fact, small magnetic field is what was considered in that paper, including h equals 0, and it's a non-trivial calculation. Okay. For determinant. Yeah.
May I ask one?
Yeah.
Yeah. So it is unitary evolution, right?
Yes, unitary evolution.
So yes. What happens when the temperature is non-zero?
So this is finite temperature. So come back. So the state I'm considering is really a finite temperature state with non-zero beta. And in this formula, you see there's beta there. And you see this log tanh looks something very natural, like free energy light type of thing for finite temperature.
Okay, thanks.
So this is our finite temperature, which was, so by the way, I should say this was quite a very important and amazing result in 1992. There was very little about finite temperature, kind of large space-time asymptotics. And so, that started actually a lot of research on that. A lot of the research was concentrated on models which has a free Fermion structure and freedom determinant and perhaps form factor analysis and all that. And recently, there's been also work on form factors which have extended this and that and have kind of clarified a bit. There are a lot of new techniques now that allow you to get that, and presumably also this was not explicitly analyzed. Okay. So there's a lot of techniques, but what I want to say is that there's a simple way from hydrodynamics that allow you to get these things, and that suppose they allow you to go beyond free Fermion. Other questions?
Can I ask a question, Benjamin?
Yeah.
So in the GG case, can I just replace BE of k with the beta I, say HJ of k, for example?
Yes, indeed. So in the GGE case, so this is a good question. So in the GGE case, this is replaced by, sum over I, what I would write beta I, HI of k, right?
Yeah, that's what I meant, yeah.
Yeah, exactly. Kind of this bit there and this bit there. But this, more complicated. There's a way, but it depends on the analytic structure of the function 1 minus, I think, e to this function w of k. So this is kind of w of k. It depends on the analytic structure of, the power minus 1. Does it have a pole? Where's the pole? And that kind of thing. So this is a bit more complicated, this bit. And the rest is simpler. So, but there is a prescription from the general theory, but not from freedom determinant yet, but from general theory there is.
Thank you.
Yeah, another question? Okay, so the first thing I want to start with, okay, so I noticed there's some monotonic algebraic decay, there's some oscillating algebraic decay. this is kind of a much simpler. It's just kind of a weak theorem, but some oscillating algebraic decay and some exponential decay. So very different type of terms in these two correlation functions. The question, what are the general principles? Right. Now, the basic general principle is the Boltzmann-Gibbs principle. And this is relatively well known, right? So the idea is essentially a linear response idea. Okay. So formally, what you say is that you have a correlation function in a large space-time. You can imagine, say, the operator at 0 to be some kind of perturbation state. Your thermal state, this perturbation travels, some waves are emitted with some velocities. These waves correspond, according to hydrodynamics, to conserved quantities or conserved densities. Okay? And so basically, the principles, Boltzmann-Gibbs principle tells you to project A onto the most QI, this QI, then to propagate this QI from 0, 0 to xt, so correlation function, then project the resulting QJ onto B. So that's kind of basic principle. Right? It's a bit just picture here, but you can write that in mathematics without too much problem. Right? So the mathematics is to say, okay, let me look at, this is some kind of inner product, some kind of susceptibility with made number K, just Fourier transform in X of the 2-point function. This is not space-time involved, just Fourier transform in X. Okay? And what you want to look at is, look at this, you want to look at this Fourier transform in X, but where one operator is time evolved, now you put a T here, right? So kind of this now becomes T. There's a little T there. And you want to look at the limit where T is very large and the Fourier mode is the wave number is very small. It's kind of the hyperbolic limit, right? So hyperbolic scaling. And the hydrodynamic projection principle, which dates from, pretty far, I mean, it was Wanzig and Mori, introduced the concept of hydrodynamic projection in various ways, and then Spohn and works use that, and then later on, I think this way of writing is the thing that I wrote in my paper, but really it's all kind of these ideas from quite far away. So what it says is that when you take that limit, where time is very large and wave number is very small, well, you can write this as projection over conserved density. So this is this zero wave number, space integrated 2-point function. Okay? This kind of projection. I mean, you can think of that as an inner product on some Hilbert space or projection in that Hilbert space. The projection involves whether there is a inner product between this basis of conserved charges, Qi, Qj, and you have to take the inverse matrix there to do the projection correctly. And then you evolve the conserved densities. This is this one where you take the limit kt, k0 to infinity of the 2-point function of conserved densities. Then you project back on B. So this is what it is, right? That's the exact formula for the little pictorial presentation that I had. It turns out that this can be shown rigorously on the appropriate definition of lim kt in every finite range homogeneous quantum spin chain, such as the XX model or even interacting one, kind of non-free-forming one. So this is a general formula that holds quite generally. Now, it's a bit kind of abstract. You take K small and T large, you do Fourier transform and all that. I'll come later on to how this gives some kind of 1/T, but that's the general formula that kind of tells you what happened at large space and large time. Okay. Now, any question maybe about this slide? So what about this 2-point function of conserved densities? Well, you can also evaluate this by, okay, so I had some remarks there, kind of a bit more mathematical remarks. So this thing gives rise to an inner product on some space of equivalence classes of observables, and that becomes a Hilbert space. You can complete that to Hilbert space. And so this is essentially the Hilbert space of extensive homogeneous observable. So there's kind of mathematical structure behind that. Okay? The time evolution turns out is a unitary operator on that Hilbert space. That's kind of non-trivial. Time evolution on the ordinary observable now acts on that Hilbert space of extensive observable. And the conserved charges are just kernel of this time evolution. So you have a precise definition of what your conserved charges of your model should be. So given a model, there's a time evolution, there's a space of excessive charges as defined in this way. And then you have conserved charges, extensive conserved charges, which are in the kernel of that time evolution unitary operator. And then the question, what is this kernel? So in integral models, it is infinite dimensional. In non-integral models, supposedly it is finite dimensional, although this is hard to show. But this is the general structure. Okay. Now, what do you do with the 2-point function of conserved densities? Well, you can just do linear response. So you write your your hydrodynamic equation and do a small perturbation that represents the insertion of a field at 0, 0, and then you want to see what happened later on at xt. And the linear response of the fluid equation, the hydrodynamic equations, becomes something linear for this small perturbation. And that linear thing involves the so-called flux Jacobian, which is just how the fluxes, the average currents in your state, vary if you changes the density. So if you add a little chemical potential associated with this density, how does the flux vary? Okay. That's flux Jacobian. And this linear equation for small perturbation translates into an equation for 2-point function. And then you get an equation, if you do Fourier transform, you get that type of equation, which you can solve easily in matrix form, just getting exponential. Okay. It turns out that this kind of linear response can be generalized to nonlinear higher point functions. In this very nice work, there's a quite systematic study of this. And it turns out that this equation actually can be shown rigorously also in finite range quantum spin chains, at least for local conserved densities. Okay. So once you have that, then you have your 2-point function, but you can rewrite this 2-point function in terms of using Fourier transform, Fourier transform kx now that directly in xt, like I was showing the result here at x and t very large, right? You can rewrite directly in xt without kind of doing the inverse Fourier transform. And the formula here that is expected to be valid, but that is not shown rigorously in any non-trivial model, is that the 2-point function at large x and large t with hyperbolic scaling should go like this projection, right? So you project your observable onto conserved density, and then instead of having this simple linear equation that you solve an exponential, when you do Fourier transform, you get delta function. So delta function of x minus at. A is a matrix. So this, of course, is delta function of a matrix. So that has to be understood in this usual sense of functions of matrices. Okay? Now, the one subtlety here that is important when you translate this whole thing into real space-time instead of Fourier transform is that you have to remember that what you actually did here when you did this, well, you take k very small, and so you do a sum over a lot of x's there. And so and the equation that you get is in the limit slash scale limit. So effectively, you do sum over you average over a large region of space. So when you want to translate that into a real space-time, you've got to do what is called a fluid cell average of your observable. There are different ways of doing fluid cell average, but here's one basic way where you just average your observable both in space and time for on some large scale. And the scale should be large enough, supposedly 10 to infinity, but smaller than the hyperbolic scaling scale, the Euler scale, in such a way that you get, essentially at the Euler scale, it looks like a point. Okay? So this is really an average over a fluid cell. So this R is a mesoscopic cell, so average of fluid cell. So this is a formula. Okay? So this is a bit abstract, quite abstract formula. You need to know what are the conserved quantities. You need to evaluate this kind of overlap, which is just space integrated 2-point function, and then evaluate this flux Jacobian, which is current with respect to densities. But once you have that, then you have an explicit form for the fluid cell average of your 2-point function at large space-time. Okay? So that's the prediction of the Boltzmann-Gibbs principle. This is kind of the main prediction. Okay? Any question about that?
Can I ask a question?
Yeah.
Sorry. Yeah, this looks like a very interesting formula, but can you think of? I mean, I'm just just a quick idea, which probably is completely wrong, but could one apply it in, let's say, XXX model for the spin transport?
Yes. So this
is no overlap. Yeah,
it's very interesting. this is a difficult question.
No, but that's,
so this is applicable to everything. XX
right.
model, spin transport applicable, but as I will show now, very often it gives 0. So very often is not useful, kind of applicable, but not useful. So if this space-time average 2-point function decay is like 1 over t, then that will give you the proper 1 over t decay. You see this delta function is homogeneous to 1 over t. Right.
Right.
So it's kind of Bonaventure thing. If it decays faster, then that would give you 0.
Right,
Then you don't do anything.
Okay, so basically, yeah, it's beyond the reach of this formula.
Yeah, yeah. And that's one reason. So I want to show different principles, which then some of these principles maybe will be applicable. But how to go beyond that? Kind of a bit limited. Okay. It's a nice formula, but a bit limited. But still, okay. Other questions? Okay, so I wanted to say, yeah, so in general, 2-point functions are expected to be supported on particular velocities, which are in the spectrum of this matrix A. 2-point functions have non-trivial structure. For instance, it can expand with some power of t. There can be oscillation. There can be all kind of structures in there. But all this structure is washed out by this fluid cell averaging. So we wouldn't see any of this alpha anything like that. We just know, okay, it goes like this, and we'll have the space integrated version of it. Yeah, it's kind of a simpler thing. Now you can apply that to the XX model. So I told you it has a free fermion structure. This is, I don't want to go into any of the technicality here. It's kind of a textbook stuff, but by the Jordan-Wigner transformation, you write your sigma plus as a free fermion, A dagger X times a Jordan-Wigner string, which is an exponential of a sum over some of large, some regional space of A dagger A, which is a fermion density. So exponential I pi fermion density times A dagger A. So you have this thing. You have a string like that, and then you put your A dagger X there, and here it's something that counts number of fermion there, and I put -1 if it's odd and 1 if it's even. Sigma minus is just the complex conjugate and Hamilton conjugate, and sigma 3 is just related to A dagger A. So it's a simple transformation. And then with that, the Hamiltonian becomes a free fermion Hamiltonian. In fact, there is a subtlety because there are 2 sectors, even an odd Hamiltonian is not exactly that. It's not exactly true that H becomes this. It's slightly different. But for our purposes, it is sufficient to write this. Okay. Now you can Fourier transform, and that's solve the Hamiltonian with the energy for each mode being 2h minus 4 cos k. So that's XX model, free fermion model, right? Now you see that sigma 3 is simple, and so we can do calculation with sigma 3. Now I want to calculate, so you can apply Wick's theorem and calculate 2-point function of this A dagger A easily. Now I want to apply the hydrodynamic principle. So what are the conserved charges? They are the C dagger C. These are all conserved, and it turns out they can be understood as extensive conserved charges in this model. In fact, they form a continuous basis for the Hilbert space of extensive conserved charges. So this is these are essentially the extensive conserved charges, the whole basis that you can take in between minus pi and pi. So this kind of fermion number at mode k. The spectrum is continuous. It's how the velocities take the form 4 sine k, and so the modes propagate with 4 sine k. So you can calculate all the ingredients of this Boltzmann-Gibbs, and what you find is, well, this can be calculated. This is equal, blah, blah, blah. I mean, just from Wick's theorem, basically. And you find that sigma 3 with qk is not 0, calculated, but sigma plus minus with qk is 0. So there's 0 projection of sigma plus minus on these conserved quantities. I mean, it's simple because there's an A dagger there and the conserved quantity is bilinear, but also because there's a string also that would give a 0. So sigma plus has 0 projection, so it gives 0, which is not in disagreement with the exponential decay, of course. But it just says that it has no algebraic decay. So using these explicitly calculated ingredients in the Boltzmann-Gibbs principle, what you find is that the space-time average sigma 2, sigma 3 takes that form. That's a form that is a specialization of what you would find in interacting integrable models, where in general you would have some function h dress there, h dress of k. You would have it squared there, and you would have some density of state rho tot of k there, essentially. But here is kind of a relatively simple in this free fermion model. You get this formula, and you get that, which is indeed the right formula that we had found from just pure Wick theorem calculation, pure calculation free fermion. But you find just the bit which is non-oscillating in algebraic, and for sigma plus sigma minus you just find 0. So it's a bit limited. I mean, it's a nice general principle. I think it's kind of very powerful for interacting systems, but it is a bit limited. You're missing a lot of terms. Okay. Any questions about this? So now, how to go beyond? Okay, so let me explain how to go beyond. Actually, I will start with the oscillating algebraic part for how to go beyond, and then I'll do the exponential part. Okay, there's 2 different principles that you can use. which are quite nice. The oscillating algebraic part, I know how to implement it in the XX model, but not yet in other models. While the exponential decaying part, we know how to implement it in various interacting models. Okay. Now, so something called fine frequency hydrodynamic projections. It turns out that this construction, kind of mathematical construction that I talked about linear products and all that, is very, very general. It doesn't need a lot of kind of properties of the spin chain to be valid. So in particular, you can replace the time evolution by anything times an oscillating term. And you can replace the space translation by anything times also an oscillating term. Sorry, not by anything. You can replace it by the old one times an oscillating term and the old one times an oscillating term. And these are still good unitary time evolution. So this one is still a good unitary time evolution on the space of extensive observable. And this one is a good unitary operator on the Gelfand-Naimark-Siegel space from which you can construct your extensive observable. In other words, you change your notion of extensivity by adding an oscillation in space, and you change your notion of time evolution on this extensive observable by adding an oscillation in time. And the whole theory goes through without a change, because the whole theory is just based on unitarity and kind of a general principle of Hilbert spaces. So you can redo the same Hydro projection, but with oscillating space-time evolution, space-time translation. So in other words, you do hydrodynamics around not k omega being 0, 0, but around some other k omega. Hydro projection around some other k omega. It's a bit formal, but formally you can do that. So the formulas, are all the same. What changes, of course, the fluid cell average changes because of that. So now you have fluid cell averages with oscillating terms. The susceptibilities that you have to calculate, they are again oscillating susceptibilities, right? That's fine, K. And the conservation condition is also different. You want the dt, the time evolution of qi, to be omega qi instead of 0. So where qi has a density with an oscillating term. So everything is a bit different. Okay? Now, this is a general formalism. If you do have such qi, then you just apply the same general formula. It's the same formula, except all these objects are all different. The q's are different, there's different space and all that. And what it tells you about the k omega space-time fluid cell averages of these 2-point functions at large scale space and time. So so this is general principles. It is in principle valid for any many-body system, for a large class of many-body system. In fact, this is kind of shown rigorously, well, not that exactly, but the Fourier transform version shown rigorously in finite range quantum spin chains. But what about an XX model? Does it give something, right? So the problem, of course, in this formulation is that you have to find such qi that satisfy this equation and that are extensive in that way. And for many values of k and omega, there aren't any. So a lot of these spaces are trivial, so it doesn't give you anything. But for some values of k omega, there may be. And it turns out for the XX model, they are. In fact, for every psi, t minus 0.4, psi standard velocity, there are two solutions, k plus minus, to the condition that the velocity is equal to psi. And from these two solutions, you can construct such a Q, a k omega kind of conserved charge. Turns out that C dagger k plus k minus is one of them. It is associated to the space omega, which is difference of energy, and k, which is the difference of k plus k minus. So this is one of these conserved charge in this fine frequency Hilbert space that you can use then to do projection. Then if you work out the thing a little bit, you work out the projection, what you find is that this fluid cell average for these particular frequencies and wave numbers give exactly the terms that we had found from wave theorem. In fact, this is just another way of doing the saddle point analysis of the wave theorem calculation. But it's a reinterpretation of this calculation purely from hydrodynamic principles. It's kind of modify k omega hydrodynamic principle. So here we get the oscillating term of this symmetry.
Can I ask you a question?
Yeah.
So your k plus minus corresponds to saddle point of your phase function?
Certainly, yes. Yes.
Okay.
That's when you do, I mean, it is exactly that, right? When you do the 2-point function calculation, you have saddle point. And you have a K plus and a K minus, and then there are terms that combine with each other that have non-trivial oscillation because of this saddle point. Yes, this is exactly.
So do you expect this in general?
So yeah, so this
For
is
other models.
Indeed. I would expect. So I should say I don't know how to do it with other models yet, although I think it's relatively clear from especially techniques of finite density form factors how that would come about. So how one could do that. But then I would expect the same phenomenon indeed.
Okay,
Right.
thanks.
Kind
Thanks.
of saddle point analysis.
Yep.
And indeed, so one thing I should say. So as you say, you look at large space-time, there's a saddle point. So of course the velocity has to be equal to this. So V of K has to be able to this size for the saddle point to occur, right? And here, why? So the concept behind this oscillatory term in the hydrodynamic language is simply that there are two solutions to the condition that a certain hydro mode be equal to the value of the velocity at which you look, the rate at which you look the constant functions. And these two solutions correspond to two creation and annihilation operators. I mean, the concept of creation and annihilation operator is not yet clear from the hydrodynamic perspective, but somehow you have these two of them. So this goes at the same velocity as that. And as a consequence, the combination still is local or extensive. Because of course, if I take, C dagger, K, C, K prime, for any K prime, that is still conserved, still fine, to satisfy all the equation with the evolution, with Hamiltonian and all that. But it's not extensive in general. That's the subtlety here.
Benjamin,
so
Benjamin, can I ask a question? Maybe trigger. Is the sum of the sigma x3 conserved?
Yes, indeed. So I didn't mention that.
No,
somehow
sure that
yes?
we're talking about. Okay, fine.
Yeah, indeed. So somehow I don't use it here, but of course you're right. So sum over x, sigma 3x is a conserved charge, which I call Q0 is the total Fermi number up to a small shift or total spin. Yes, it's conserved charge. So here I'm not using that explicitly. I don't need to use that. Of course, here I am using aspects of this because I need to calculate the projections, and I'm using the free Fermi social to calculate projections. And supposedly you can calculate these projections when these are conserved charge a bit easily, but more easily. But they're not explicitly using this. Other questions?
I mean, that means that the Euler equation for sigma x3, is it closed in sigma x3 or is coupled?
No, indeed, it is coupled. It's conserved, but it's coupled. It's the GHD. So you cannot extract it as a single hydrodynamic equation, as a small system of a hydrodynamic hyperbolic equation, even if it's conserved. It is coupled with everything else. So it's still, it's still a non-trivial object from that perspective, if you will. So you wouldn't expect a standard hydrodynamics phenomenology for this two-point function.
Okay, thank you.
It's more the GHD phenomenology. Yeah. So from that perspective, it's still much more like, more like a generic local observable, So that's the situation.
Benjamin,
yeah, go ahead.
Yeah. So I guess the X magnetization, of course, is not conserved, right? So that's why it decays exponentially. And I guess from hydrodynamics, one wouldn't expect to be able to compute it, or
indeed. So the X magnetization is not conserved. Now, it is not. This is not necessarily why it decays exponentially, because there are many things like I don't know, like sigma 3x, sigma 3x plus 1. This is not conserved, I think. I didn't check it, but something is not conserved in general. But that would have a similar phenomenology as that sigma 3. Okay, so it would have a 1 over t decay at large time in time-like regime. It will have some oscillation, and the oscillations, it will be possible to calculate them using this kind of projection. Haven't done a calculation yet, but it will be possible to do that. So it will have similar phenomenology, although it's not conserved, just because it's some local observable that projects onto the conserved quantities. Right? The only thing is that it's got to be able to project onto conserved quantities.
Okay. Yeah.
And it turns out sigma x does not project onto these extensive conserved quantities. And so why? I mean, it is related to a bit the question that Thomas was asking about in Heisenberg chain as well. You have small, strange, kind of different large space, large time behavior of 2-point functions. And somehow there are certain observables whose behavior with respect to conserved quantity is very strange. So here it doesn't project onto. It is related to the idea that it's kind of an order parameter. That's kind of the idea behind that. Although it's a bit like this, the spin easing model in the ordered phase. So at 0 temperature ordered phase, the spin takes either value up or down in the easing model. At finite temperature, well, it takes value 0, but it can be seen as it takes value 0 because there's a lot of up and down domain walls that fluctuate, and that makes it 0. And this fluctuation of domain walls is what gives exponential decay. Actually, I'm going to come to that. Other questions? Okay, so that's the oscillating term. There's an explanation, hydrodynamic explanation. But now I want to go to, indeed, exactly your question about the exponential decay. Okay, so this is now a different type of phenomenon. Of course, different. Here we use projection. The projection can always just give Heisenberg decay. So here there's no projection at all for exponential decay. So what can we use? What's happening? Okay. Well, there's a notion of a twist field, which is a very much used notion in quantum field theory in particular, and has various applications and all that. But here I want you to use it solely from the concepts of hydrodynamics. It can be introduced in this context only. Okay, using this within this context. Okay? So what is a twist field? Well, formally it can be thought of as an exponential of a formally defined height field, a height field that solves the hydrodynamic equation. No, or more precisely, not the hydrodynamic equation, but the macroscopic conservation laws. Okay? So you write your macroscopic density as a derivative of something, and your current with respect to x as a derivative with respect to time of something, and of course, then this automatically satisfies the continuity equation. Okay? So this is a formally defined field, and what one is interested in, the twist field is the exponential of that, and you can do other things with this, but exponential is interesting. Okay? And in particular, what makes a lot of sense is to look at 2-point function of such field. So e to the minus lambda phi I xt, e to the lambda phi I 0, 0. Now I've put them together in the exponential here. Okay? Now, if you put them together in exponential, what you see is that actually this difference of phi is nothing else but an integration of the 2 current on space-time from 0, 0 to xt. So essentially, you integrate this 2 current with the appropriate epsilon, nu in space-time from 0, 0 to xt. And by writing this, it just becomes the boundary terms, right, of this integration of the 2 current. Now, because this is a conserved 2 current, actually the shape of the path does not matter. And that's one reason why people usually say that this kind of field is local in some sense and supported at xt00. This is not some field that is some operator that's supported on the whole path, because actually the path, you can change its shape as much as you want. So it's not really supported where the line of this integral is, because you can change the path, but what you cannot change are the boundary points, so it's supported there. In a lot of calculations, indeed, it is very useful to change the path, and you see that, yeah, you can really bring it far from any other field, and it's like if there was nothing there. Okay. So this is a bit formally defined field, but more precisely, what you're looking at is exponential of a space-time integral of 2 current on the line. Okay. Now, why doing that? Why not? Okay. But why doing that? Well, the connection with sigma plus is via the Jordan-Wigner string. Jordan-Wigner string tells you that sigma plus is some a dagger times exponential of I pi, a sum overall position from 0 to x minus 1 of some fermion density. Now, this is conserved. So this is really what I would call, say, Q0 of y, okay, and time goes 0 here, okay, is the conserved fermion number of that model, right? So that has the shape of this kind of thing that I was telling you about with a path like that, but the path would be just purely horizontal, right? From kind of x0 to from 0, 0 to x0 kind of, right? So that thing, right? But you could imagine then that maybe we should identify sigma x plus of t as the time evolve of the fermion with one of these e to the I pi phi. So you have here the whole line integral starting somewhere. So you can imagine, well, okay, it doesn't depend too much on the path, and so it's kind of the field xt. And there's a lot of, there's actually a great many subtleties in there, because in fact this starts at 0, but the point 0 in the Jordan-Wigner transformation is a bit special because it's the point where you might have periodic or anti-periodic boundary conditions and all that. So by a manipulation, what you can show, actually, show or argue, not show completely, but argue, you can show something which is stronger, but you can argue quite strongly, that the two-point function indeed takes the form of some fermion there and a two-point function of such twist field, so an exponential of line integral of two current and a of 0. So essentially, this is a space-time Jordan-Wigner string. Okay. Now, such things have been written in the past many times, but especially in the context of classical statistical mechanics, where you have a 2D lattice, and then you have this Jordan-Wigner string, which is just a sum over a lot of observables on your 2D lattice, anywhere in the 2D lattice, not just in horizontal, but anywhere. Okay. So this is the real-time version of this. So it's not 2D lattice, it's a quantum model. It's a real-time version of this. It is not, as far as I understand, not an equality, but it is true in a sense of asymptotic behavior. So that's my. It's not an equality. There is an equality that you can write, but it's not exactly in terms of these fields. It's something related to, but similar, but slightly different. That involves an integration of current and integration of densities. So my understanding is that this is not an exact equality, but true in the sense of leading exponential behavior. Okay. There are subtleties if you want an equality. There are things that don't commute because it's quantum, things that don't commute that you have to take care of and all that. Okay. But you can write something. In principle, you can get kind of next order and all that. Yeah. Okay, so questions about that. So this looks like the type of thing you want to calculate up to these boundary fermions that are there, right? So this additional structure in this actual sigma plus sigma minus observable, right? Now, let me think before this additional structure about just that, okay? So can we get a leading exponential decay from that? So the idea here is that what we see is that this looks like a two-point function, which if this was not there, this two-point function will just be standard two-point function with standard algebraic decay and all that. I mean, one can do saddle point analysis nowadays. Okay, but there is this extra string, Jordan-Wigner string, which is non-trivial, which is kind of a whole integration over space-time, although it's not path dependent. And that will somehow change a lot what this two-point function is. And this is the basis for the exponential decay, for the main part of the exponential decay. Okay. So how do we get this exponential decay? Well, okay, let me think about this type of object in general. Yeah? We want to specialize to lambda equals I pi and to JQ being the fermion density, fermion current, but we can think in general. Okay. So the idea is relatively simple. Is just to look at that. This is an average of exponential of lambda, something that looks like something where we can apply large deviation theory. Right? So we want to take L here large, do the hyperbolic scaling, and so we can say, well, perhaps large deviation theory applies here, and what we get when L is large is exponential of L times something. So that will grow or decay depending on lambda, depending on the details, like exponential of L times something. Okay, so you can think of that also if this lambda here is just some general parameter. If you expand in lambda, that would be the generating function for the cumulants of this particular random variable as part observable. And what that would say is that all the cumulants scale like L. Now, maybe this is true, maybe it is not. That will depend on structure. But in fact, what I want to say is that in many cases, this is true. And this can be calculated. And it can be calculated solely using hydrodynamic or other hydrodynamics of the model. So it turns out that this quantity is a hydrodynamic quantity. So an exponential decay can be hydrodynamic. So the idea behind is that what you want to calculate are cumulants of some observables, some densities and currents, right? Cumulants are correlation functions, and you want that at large scale of space-time, so you can use Euler hydrodynamics. So in principle, you could use kind of higher order nonlinear response theory order by order to calculate all those cumulants, in principle, and using Euler hydrodynamics. But here you can directly calculate this by other techniques without having to expand it. Okay. So that's the idea. So calculate this from Euler hydrodynamics and apply it to this 2-point function. Yeah, okay. So this is something that we call ballistic fluctuation theory we developed in 2019. So the basic idea, I don't want to go into too much of the details of that, but the idea is relatively simple. It just says that, well, if I insert this exponential of lambda, I can think of that as biasing the measure or changing the state. It's something that's been used quite a lot in the study of large deviation theory, in particular for classical system. So you bias the measure by introducing this, and then you ask, what is the new measure? What is the new state? One can argue, and that's because the shape of this curve is irrelevant. You can move this curve as much as you want. So one can argue, because of that the resulting state is homogeneous and stationary. So it's independent of space and time. If this was not conserved two currents, that wouldn't be the case. But because it is a conserved two current, that's the case. Okay? And because it's homogeneous in space and time, then you can also argue, but that's a bit more difficult, but at least order by order in lambda, you can argue that the state is clustering as well. And for clustering homogeneous stationary state, what it could be is only a GGE. So you can argue that this state is just a GGE that has its own betas. And then by using hydrodynamic projection, by taking lambda derivative and using hydro projection, the basic hydro projection that I explained, you get a flow for this d lambda beta. And that's the flow equation. The flow equation tells you that these beta for this GG change as you change lambda. And change in a certain way, you just have to take the sign of a matrix. The matrix is X times the identity matrix minus T times the flux Jacobian evaluated at that state. And you take the ij. So I here is the thing that I put in the measure, and j is the thing that characterizes the GGE. So that changes the state from thermal to something much more complicated, some GGE with a lot of betas and all that. Okay? So that very much depends on what are the betas available for your model. And maybe the GGE has it's a generalized Gibbs ensemble, lots of betas. Maybe it's a non-integrable models and there are just 3 betas. And in principle, that still is valid. So this formula is valid for generic many-body systems. Okay? So that's the situation. And once you have that, once you have this state, then basically this quantity is basically a free energy or scale cumulative generating function, but it can be thought of as a free energy, and you can evaluate it by integrating over lambda the average current in that state that flows with lambda and the average density in that state that flows with lambda, putting the t in the x. Remember that t in the x is how I do my large scaling. L is large, and I have t in x that specifies where I am in space-time. Okay. So that's the situation. That's an exact formula, in principle valid for any models where you have available in Euler hydrodynamics. So that tells you kind of a lot about cumulants of current and density. But here we want to apply it to the XX model. And the XX model, because this is integrable, but more than that, has a free Feynman structure, it is much, it's very simple. The result of that is very simple. The flow equation can be solved exactly. You get this and that. Now, this looks a lot like the formulas that I had written for the asymptotics of 2-point function sigma plus sigma minus, right? X minus vt, some log of something that looks like a free energy. Okay? So this is just flow equation specialized to XX model for the expert. I mean, the flow equation in general will have a d lambda of epsilon, where epsilon is the free energy, and that's going to be equal to sine of blah, 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 where you have effective velocity there. And this will multiply by hi dress. Yeah, so x minus t effective velocity, hi dress. So that would be the kind of for integrable system, but for the XX model, it simplifies drastically to that form. Okay. So now I can just apply that to the evaluation of correlation functions. There's one more little step actually, because remember that I had this A dagger A at the boundaries, and the one more little step actually, this is something that was stopping us for quite a long time to go further, Well, it turns out that can be factorized that way. So the 2-point function sigma plus sigma minus is controlled by this large deviation function or scale cumulative generating function coming from large deviation of transport of this conserved quantity that, well, of number of fermions. So this is spin transport fluctuations. And another term, which comes from these boundary fermions. And this other term is nothing else but the fermion correlations evaluated within the GGE that is obtained under the flow. So the flow changes the state that you have there. And the leading asymptotic decay, exponential decay of correlation function of fermions is just controlled by that GGE that's inside. So you have spin fluctuation there and correlation functions of local operators in a lambda dependent state, a weird state. And here I want to take, of course, lambda equals I pi. Now there's a bit of a subtlety about continuation to I pi, the complex values, now that one can deal with it. And then in the end, all one has to calculate is this 2-point function, and that is formula already given. When you do that, you get exactly this, which is the things that were obtained previously and the new thing that we have obtained. Right? So this bit comes from the large deviation theory, and this bit comes from the extra 2-point function of fermion factors. So, and this extra bit is calculated by Wick theorem and by saddle point analysis again. So that one has to do kind of a, if you wish, Hadron projection again. But, well, not Hadron projection, but Wick theorem and saddle point analysis. Okay. So that's the explanation of this 2-point function of spin field, sigma plus sigma minus in the XX model. I think my time is up. Yeah, so that's essentially what I wanted to say. So we have now kind of hydrodynamic explanation for all these correlation functions with all these different behaviors, including oscillating, including exponential. So the exponential here is seen as coming from fluctuation, so the main expression from fluctuation, this kind of scale cumulative generating function, kind of measure fluctuations. Fluctuations of what? Well, so, yeah, it's there. Fluctuations of spins. So if it's purely time, then it's a spin transport, because you look at the current. If it's purely space, it's total spin. So you look at fluctuation of total spin within a region. And this spin fluctuations is, so why the sigma plus sigma minus are related to spin fluctuation. This has to do with interpreting the sigma plus sigma minus as some kind of order parameter for this model. In fact, I expect this kind of thing is general for order parameter of various types, where you have domain wall fluctuation in finite temperature, and this kind of domain wall fluctuation is what gives rise to exponential decay. This kind of idea was used actually in the past for getting kind of approximation conjecture or approximation of this kind of exponential decay for using model, in particular by Sachdev in the 1990s. I don't remember exactly now, where he was exactly looking at fluctuation of domain walls. But here we have an exact theory using hydrodynamics that gives us the full thing. Okay. So that's it. Here's numerics comparing, because the last formula was never established kind of rigorously for macroscopic, but we've checked it numerically. So this is magnetic field that changes, that's various temperatures, and everything works very, very nicely. And that's all I wanted to say. So, okay, two different things going beyond Boltzmann-Gibbs principle. Fine frequency hydroprojection. Actually, this is related to dynamical symmetries that were used to bounce some kind of fine frequency through the weights in these papers and others. I mean, this is just some of the papers that have been studied. So there is work on that where this is done not just in a free fermion model, but in an actually interacting model where you find special symmetries that oscillate and that can be used to bound oscillating through the weights. And I expect that this can be extended to integral models using finitely form factors. The question, is there some finite frequency hydrodynamic equation? What about higher point functions? And as for the twist fields, well, it is immediately applicable to sine-Gordon model field of this type, actually, because we have all the tools already. We have the GHD, we have the general formulas for decay, for large deviation decay. So this is directly applicable. We're looking into that right now. Potentially applicable for the psi field and Liebniger model, although perhaps a bit more complicated. It can be used to study non-conformal dynamics of entanglement entropy, because entanglement entropy can be represented using twist field as well. So this field is very powerful. And it's connected to macroscopic fluctuation theory, which is something that Keiji is going to talk about tomorrow, I believe. So this ballistic fluctuation theory is kind of some kind of the little brother of the more flexible macroscopic fluctuation theory as applied to ballistic transport, and that we are now working on with Takato and with Sasamoto. So and that's it. Thank you for your attention.
Okay, thank you very much for the very nice talk. Are there any questions, comments? Okay, so first, Will, please.
Hi, thanks for the talk. I had a quick question on the definition of twist fields in the generic case. So it seems to me you're assuming that the flow is smooth on some domain. So do you need to worry about shocks at all in defining that kind of integrating factor?
Yes, yes, indeed, yes. I need to worry about shocks and that. So let's see. Well, okay. So what I'm assuming that this is some. I'm assuming something here, okay? That it grows like L. And I believe that indeed shocks can change this type of behavior. And in particular, so let's see, look, there is this kind of X and T, and you're looking at cumulants, say, along a certain line, right? Cumulants of currents and then still along that line. Now, so the main thing about that is that the cumulants should all exist. So the many point functions where you have, say, Q at 0, 0, and then Q at X, T, and then Q at 2X, 2T, and stuff like that. And suppose you integrate over these, you look at large space-time of this fixing one. So that kind of many point function integration over X this is not the right way of writing, but integration over the line, that should exist. So there's an assumption that cumulants exist. So that Gaussian function exists at large space-time. And this assumption is expected to be broken if you have hydromoles with a velocity that is equal to this X over T. So in generic hydrodynamics, this is expected to be broken. And then that form will be broken, and then something else is happening. And we don't know exactly, but in principle, we can analyze with this macroscopic fluctuation theory, but not with that theory in particular. Okay, but it turns out that for integral models, it doesn't matter, and I think that's related to the fact that integral models there are no shocks nowadays. So it turns out that integral models, these intervals still converge, and everything is fine. So for non-integral models, the theory applies and is nice up to the point where you may reach this kind of velocity where you have a modes and then something else happens and then you need to deal with that. So this is related to non-equilibrium phase transition. Essentially what you have is a non-equilibrium phase transition. It's something that people also have studied where there's a sudden change in the structure of large scale cumulants. Does that answer your question?
Yes, thank you.
Yeah.
Thank you. So next, Abhishek, please.
Hi. So I had two questions. So the first is, sort of a general question. So normally in usual hydrodynamics, like supposing we have a microscopic system and we don't know how to compute correlations, then of course, like we go to hydrodynamics and write, but there we have to write fluctuating hydrodynamics, and that allows us to compute correlations, right? So here it wasn't clear to me, like if you're writing a sort of, if you're including fluctuations in your equations.
So that's, thanks for the question. This is excellent. So indeed, this is the way that is usually done in the statistical mechanics, right? So it allows it to calculate Gaussian function by putting fluctuations. But the general Boltzmann-Gibbs principle tells you that actually you don't have to do that. So here I did not. There's a whole bunch of results that I've presented. Some are kind of almost rigorous or rigorous. Some are very far from it. Okay, so some are intuitive and all that. Okay, but the Boltzmann-Gibbs principle that I presented at the beginning, just the main one, the basic one, this can be shown rigorously in the form of a Fourier transform in quantum spin chains where you don't introduce any noise. I mean, this is a quantum spin chain. There is a state which is density matrix and all that. So you never introduce any additional noise. And the result is this projection over conserved densities. Now, you can also obtain that same result by adding noise and calculating correlations, you will obtain the same thing, right? But here what I'm saying is that it's not necessary to introduce a posteriori noise or phenomenological noise in order to get to this kind of hydrodynamic projection. This is a result that is valid also in quantum systems, as derived from macroscopic. I mean, the theory that one uses is the sister algebra construction of a quantum spin chain, essentially, and that some basic aspect of that, and you can derive that. So you never have to introduce noise. The result is you take your observable, project it over densities, evolve the densities, project back the other observable, and the evolution of density follows the hydrodynamic equation. Yeah. While for this large division theory, I mean, again, I don't explicitly introduce any noise here. I mean, this is just a calculation of cumulants, if you wish, using earlier hydrodynamics.
Okay, and one other very quick question is like, so if you compare the hydrodynamic calculation and the microscopic calculation, I mean, does it actually simplify life? I mean, the hydrodynamics.
To do the hydrodynamics, so it depends, right? So here for the XX model for sigma 3, it doesn't, right? I mean, because
okay, but for sigma X it does, I guess.
For sigma plus sigma minus it does a lot. I mean, for sigma X, I mean these results are rather non-trivial to obtain for microscopic. They're possible to obtain. As I said, these I know they've been obtained, and these we haven't seen in the literature, but they can certainly be obtained from the techniques. But it's quite involved techniques. While for the XX model, all this large division theory is kind of trivial.
Okay.
Now I should say one more thing, is that in the results that are obtained, like by this paper by Itz and Troy and other people, they go beyond that. There's also a prefactor, like t to the something that they can obtain from the asymptotic of the Freedom determinant. That here I don't know yet how to get from hydrodynamics, but supposedly maybe you go to next order hydrodynamics. So there's still quite a bit of open questions, but yeah, simplify. And the other thing, so if I try to do a sine-Gordon model, e to the I phi of x comma t, say with an alpha there, e to the minus alpha I phi 0, 0, that's a 2-point function in sine-Gordon model, perfectly well defined. Nobody has ever written a asymptotic exponential asymptotic formula for that. It's an integrable model, quantum field theory, or you can discretize it by turns out, but nobody's written this exponential decay. Nobody knows how to do that. While here we have a conjecture from hydrodynamics. The conjecture is complicated, but calculable. Yeah.
Okay. Yeah. Thanks.
Yeah. Good questions.
Okay. Next, Junji.
Oh, thank you very much for a very nice talk. That's very interesting. And my question is, your new formula concerned with space region, if I understand correctly.
Yes.
And for that case, I mean, there is some result about the prefactor.
All right. So about the prefactor you here, that multiplies the exponential.
Right.
But so maybe I ask you then, because I think you are an expert. Are there results? So we didn't see results for h greater than 2.
Ah, okay. So h is greater than 2. Oh, sorry. Yeah. I mean, I didn't see that.
Yeah, yeah.
Uh-huh.
So we haven't seen that for h smaller than 2. There are results, and there are results for prefactors. So the prefactors we did not obtain them from hydrodynamics. We don't know how to obtain them, and the macroscopic formulas, of course, you do obtain them. Yeah. But what we could obtain is h greater than 2, where there's not only this usual exponential decay, but another exponential decay, which we interpret in our construction as coming from 2-point function of fermions, which we calculate as 2-point function of fermions using Wick theorem.
Very interesting. Very interesting. Okay, so I think, I mean, yeah. Okay, anyway, thank you very much. I'm very interested.
Okay, so Alitra, please.
Hi. So I wanted to ask, maybe you mentioned, I missed it. I mean, in the twist field, the structure of the twist field has a universal structure across various integrable systems. Is that
Yes.
true? So
Yes,
given a like integrable system, one can directly write it down the structure of this twist field.
Yeah.
Okay.
So the structure of the twist, it depends a bit what you mean, but one can write down the field as actually this is a general principle. As soon as you have a symmetry with a local conserved current, now that you can write a twist field associated with it, and that holds in quantum many-body system quite generally. And then what I showed there with this large division theory, where there is an asymptotic for exponential decay of such twist field, which is indeed quite a general structure for integrable systems. One can write a formula based on TBA. It's actually a complicated formula. I didn't write it, but a formula based on TBA, and that should describe the leading asymptotic decay of such twist field.
Okay. Okay. And the other question is can one compute higher point correlations from this, or is it?
Yes. So that's an excellent question, and I don't know yet. This is something to be looked at. I believe so. Yes, I believe so. I think the twist field, the higher point correlation function of twist field, has been looked at in other contexts, like in CFT or in at zero temperature, and I'm pretty sure that it is possible. There will be a similar kind of large division principle, but of course you can imagine if you have many points in space-time and many lines now that the state would be rather non-trivial. But I'm pretty sure it can be done with appropriate analysis, hydrodynamic analysis. I'm quite sure. I mean, Hydro can do really a lot.
Okay. Okay. Yes. Thanks. Very interesting.
Okay, thank you. So there could be some more questions, but I think it's time to stop. So let's thank Benjamin again. Thank you very much, Benjamin.